anything you need to look at?
Took me 6 hours to do probability and
number
statistics.
5 from chapter 16.
6 hours to do probability and statistics? Probability is fun, right?
So I figured out how to set it up. That's the hardest part.
But once you get the solution, it's fun. It's fun just to see how probability works.
Yeah, it was neat.
Yes. Take a look at number 5 in chapter 16. It says an earthquake emits both S waves and P waves, which travel at different speeds through the earth. A P wave travels at 9,000 meters per second, and an S wave travels at 5,000 meters per second. If P waves are received at the seismic station 1 minute before an S wave arrives, how far away is the earthquake? Here's a theoretical Earth. I'm getting worse and worse with that. And somewhere there's an earthquake. And the earthquake, there's basically two waves. There's a transverse wave that travels. So it travels kind of like this. And that's the S wave. And there's a longitudinal wave, kind of like a spring wave that travels. And that's the P wave. And they both travel at different speeds, and they both travel differently through different matter. P wave can travel through solid and liquid. I think the S wave can only travel through solid. So that's one way that you can use earthquakes or other seismic activity to figure out what the interior of the Earth is like. Because you study these waves and you can see where there's solid matter, where there's liquid matter, and that sort of thing. In this case, though, we're told that the velocity of the S wave was 5,000 meters per second, and the velocity of the P wave was 9,000 meters per second. Right? And we're told that at a particular seismic station, P waves are received 1 minute before an S wave arrives. Let's say we have a seismic station right here. And let's say that it's a pure distance, D, away from the earthquake center. And we're told that the time for P wave is equal to the time for an S wave minus 60 seconds. Because the P wave arrives 1 minute before an S wave arrives. And so we want to find out what that D is. Right. One way to do that is since they're both going to travel the same distance, and we know that the distance will be the velocity of the S wave times the time for the S wave, and the distance will equal the velocity of the P wave times the time for the P wave. So we could say that since distance equals distance, the velocity of the S wave times the time for the S wave equals the velocity of the P wave times the P wave. So the time for the S wave equals the time for the P wave divided by the time. I want to do it this way. Velocity of the P wave divided by the velocity of the S wave. This would be 9,000 going to plug that in to this. So time for the P way, take on time for the S way, minus 60. So time for the P way, take on 1.8, time for the P way, minus 60. Or bring the 60 over here and bring this over there. 0.8 time for the P wave equals 60. Time for the P wave equals 60 divided by 0.8, which is, we got 75 seconds. Nice to know, but we want to find out the distance. So what we'll do is put that into this. Since the distance is equal to the velocity of the P wave times the time for the P wave, that'll be 9,075 seconds. 9,000 meters per second, which would be 675,000 meters. Or 675 kilometers. What do you think? It's a little bit of a seismic activity this morning. Anything else you want to look at first thing here? Chapter 15, chapter 16. I'm actually going to give you a sample test today. So, yeah, because your first test is a week from today. So if I give you the sample test today, then we should have time on Monday to go over it. And hopefully you would have time over the weekend to go over it. So, ready for something new? Already? And we have a lot to talk about today. I want to talk about the Doppler effect and also venture a little bit into chapter 18. So I'm going to finish up chapter 17, venture a little bit into 18, finish 18 on Monday, and go over the sample test. And then we'll be ready for this first test with your 3x5 card. 4x6 car. 4x6 car. Maybe 5x7 by that time. Oh yeah, one more thing. What's in the news today? What is an important event that's going to occur today? You know what that is? People have been talking about it for months. It has something to do with physics. It's not just that Ohio State's going to be ranked number 1. Which would be a very important event. What's that, Christy?
Is it when they were going to try and recreate the Big Bang Theory?
Yeah, it's related to that.
It was
What?
large for a long time.
There's a facility in CERN, or a CERN facility. It's on the border of Switzerland and France, and it's kind of nestled in the Alps, where they've set up a real large collider, and the idea is that they're going to accelerate protons to speeds, well, very close to the speed of light, like 99.9999% the speed of light. And you can't go faster than the speed of light. At least we haven't been able to achieve that. It's theoretically that's not possible, but if you accelerate these particles to that speed, you need a lot of energy. Let's actually, I think I kind of have the Google Earth set up for this. See if I can click on Google Earth, and we can look at. There we go. There's a live feed of this facility in Switzerland. It's on the border of Switzerland and France. This is the CERN facility. It's kind of underneath all that. And so the idea is today they're going to turn this on. They're going to collide these particles, and it's going to require energies on the order of terajoules. Okay? And one reason, normally, what's that, tera? Tera is like 10 to 15 joules. Nothing like this has ever been done before. Right? And normally a physics experiment like this would not be of any kind of news, but there are some people suspect that there is some danger involved in this. All right? The idea is that if you collide these particles at these great speeds and these great energies, you will create possibly a black hole.
Will it make France disappear?
What's that, John?
Will it make France disappear?
Maybe France will disappear. So I don't know, whether that's the bad thing or not. Just kidding.
What's the purpose? It's just
Well, the purpose is to investigate the properties of the proton and see what actually makes it fluid. Somebody's calling me to warn you about this.
I'm sorry.
That's all right.
Some people theorize that black holes there's a connection to black holes and time travel.
Right.
So
So it could be a good thing. So if we create this black hole, you just have to travel to France and you can go back in time. So actually, one thing I wanted to show you live feed, it's kind of cool, that it was supposed to be turned on at about 8:20 our time today. So that's like within a minute or two of right now. So it's kind of cool. Now if this, but if this has been talked about for a while, and this could be, if some people are correct, which they shouldn't be correct, this could be the last day of your life. Right? Because if it creates a black hole, then we'll all be sucked in, and that could be it. So, but really, if you think about it, the Earth is being totally bombarded by energetic particles all the time. Oh my gosh! Oh, Mom. I can't believe it. That didn't get you at all, did it? You knew that was coming. Did you know that was coming? That took you too long to say that. Actually, I thought that would be funny. That's actually a fake desktop and everything. Actually, to be honest with you, Jimmy Duke, the natural science director, was the one who did all the swirl. He did the Photoshop stuff. So I just kind of put it into animation, put it together. Didn't take that long. But today is the first day that they're going to turn it on. So, but I was going to say that just to allay your fears, the Earth is being bombarded by terajoule particles all the time from outer space, and we're still here. So it's probably not anything to worry about. Just update your will or something. No, really seriously, not anything to worry about. It'd be kind of cool to see what happens. So today we're going to talk about the Doppler effect. Here's one idea with the Doppler effect. In general, the Doppler effect is experienced whenever there's a relative motion between the source and the observer. If the relative motion is toward, then the observed frequency will be higher. And if the relative motion is back and away, then the observed frequency will be lower. All harmonic waves experience the Doppler effect. So this is something intuitive in your everyday life that you've observed and you have knowledge of. This Doppler effect. You've seen it happen, you've heard it happen. Probably haven't seen it happen, but it can happen to light as well. But you've heard it happen in your everyday life. So you know that if two sources, if a source of sound is moving towards you in some way, in a relative way, but moving towards you, that frequency of that source goes up. And if it's moving away from you, it goes down. That's your intuitive feeling about the Doppler effect. How might this work? Let's think about this. Let's assume I've got a source here. Actually, I'll put the source over here, just like my diagram. Let's say it's putting out waves. All right. These waves are coming towards me, and the waves are hitting my eardrum, making my eardrum move back and forth. And so I interpret that frequency of that wave. And my eardrum actually mechanically moves back and forth with the same frequency as the actual wave of the source is putting out, if I'm at rest and if the source is at rest. So I actually hear the true frequency of the source. Makes sense? But what would happen if I were to start walking towards the source? These wave fronts are coming in. Normally, if I stand still, I hear the true frequency of that source. A wavefront just came in, and now I'm going to start walking towards the source. So the next wavefront is going to hit me a little bit sooner than if I had stood still and stayed where I was. So that one hits me a little bit sooner. My eardrum gets that wavefront a little bit sooner. And then I continue walking towards the source, and the next wavefront hits me a little bit sooner as well. So what happens is, essentially, with these waves coming in, if I walk towards the source, I am going to increase the frequency that I receive these wavefronts by receiving them sooner as I walk towards the source. Makes sense? Effectively, I'm going to increase the frequency by receiving them that much sooner as I walk towards the source. Mathematically, it could look something like this. If the source is putting out a certain velocity of sound, which we've designated just by V here, and I have a velocity, the velocity of the observer, I've effectively increased the velocity of sound by my velocity. So by moving towards the source, the sound that I receive is the true velocity of sound in air at this temperature plus my velocity. and hence the frequency I think I hear, or that appears to me to be the frequency, is that velocity divided by the wavelength of the sound, which with a little bit of algebra looks like this. The frequency that I observe is equal to the actual frequency put out by the source times this expression here, which is 1 plus the velocity of the observer over the velocity of sound. 1 plus the fraction, the velocity of the observer over the velocity of sound. Well, if I'm the observer, let's say it's putting out a frequency of 400 hertz, for example. I'm the observer. Let's say I start moving towards the source at 1 meter per second. What frequency do I observe? Well, according to this formula, I would observe a frequency equal to the 400 hertz times 1 plus the fraction of my velocity over the velocity of sound. This would be 1 over 343. Because we said the other day, the velocity of sound, unless otherwise specified, at room temperature and air is 343 meters per second. That's a really small fraction. 1 divided by 343, that is so small as to be almost imperceptible as far as the difference is concerned. If I'm moving at 1 meter per second and it's putting out 400 hertz, I'm probably going to hear very close to 400 hertz. So at that speed, I won't hear any difference in the source. But if I'm moving at 60 miles per hour, which would be approximately 30 meters per second, let's just say 34 meters per second just for argument's sake, then this fraction would be 34 over 343, so this fraction would be about 1/10. All right? And now, my observed frequency will be equal to the actual frequency 1 plus 1/10. In other words, my observed frequency will be 10% higher. So instead of hearing 400 hertz, I might hear 440 hertz. On the chromatic scale, that could be 2 notes on the chromatic scale. So instead of F on the chromatic scale, I would hear A on the chromatic scale. That would be at 60 miles per hour. If I were moving at 60 miles per hour toward that source. So it goes up 2 notes on the chromatic scale. What would happen if I were moving away from the source? The source is still stationary. I'm walking away from the source. Let's talk about that situation. Normally, if I were standing still, I would receive these wavefronts that come in. They move my eardrum back and forth, and my eardrum would move back and forth with exactly the same frequency as put out by the source, so I would interpret that exactly as the frequency of the source. These wavefronts would come in like this. But I just received a wavefront, next one's coming in, and now I'm moving away from the source. So it actually took a little bit longer to get to me. I finally received it over here. I continue moving away from the source. The next one after that, I finally receive it over here. Effectively, as I move away from the source, the frequency of the wavefronts that I receive actually goes down. Because it takes a little bit longer for those wavefronts to get to me. So as I move away from the source, the effective frequency that I hear is less than the actual frequency put out by the source. What I could say is by me moving away, I've reduced effectively the speed of sound by the actual speed of sound, which would be v, which we would know to be 343 meters per second, minus my velocity, whatever that is. So, the observed frequency with a little bit of algebra is the actual frequency times 1 minus the fraction of my velocity to the velocity of sound. again, if I only move at 1 meter per second, which is actually pretty good walking pace, I'm not going to observe any difference in frequency. That fraction is going to be too small. It's going to be 1 over 343. For all practical purposes, I'm still going to hear 400 hertz if it's putting out 400 hertz. But if I'm moving at 60 miles per hour this way, let's say 34 meters per second, then that fraction again will be 1/10. And so we'll have 1 minus 1/10, or making this 0.9. So effectively, I'll be reducing the frequency that I hear by 10%. And so if it's putting out 400 hertz, I now hear 360 hertz approximately, which would be 2 notes on the chromatic scale in the opposite direction. So if it were putting out F, then that would be E on the chromatic scale. So, if that's the source, and I'm moving, and I'm the observer, and the source is putting out F, then what I might hear is something like this. Can I hear that again? I thought I heard a siren in the background. That's fun. But you've experienced that, right? Where it seems like frequency goes up, and then as you're moving away from it, frequency goes down. And really, it would be a quick transition as I pass the source. As I have the higher frequency down to the lower frequency.
Frequency going up is going to get closer.
Well, that's the other situation. That maybe the observer is not moving, maybe the source is moving. But you'd have a similar effect. Bear with me. All these formulas that we're giving you here is going to all be summarized into one formula to rule them all at the end. Here's what would happen if the source was moving towards you. If the source is moving towards me and I were stationary, the source would be putting out wavefronts in successive order, but as the source moves towards you, it's putting out wavefront here, and then puts out wavefront here and one here. So effectively, even though its frequency hasn't changed, effectively its wavelength is shorter because the source is moving towards you, it's putting out a shorter wavelength. The wavelength is shortened by a distance equal to the velocity of the source times the period of time that it puts out those waves, which would be the velocity of the source divided by its actual frequency. So we would have an effective wavelength of the actual wavelength of the sound minus this wavelength due to the motion of the source. And there's a lot more algebra involved here, which I'm not going to explain, but it's in your notes. And ultimately, we come up with this nice result here, that the effective frequency that an observer would hear as the source is moving towards the observer is equal to the actual frequency put out by the source times the fraction of the velocity of sound over the velocity of sound minus the velocity of the source. If the velocity of the source were slow, 1 meter per second, then this fraction is still very close to 1. I would have 343 over 342, which is basically very close to 1. I would observe a frequency very close to the actual frequency of the source. Not much difference. But if the source were moving towards me at 60 miles per hour, then this velocity of the source would be about 1/10 the velocity of sound, and hence we'd have something over about 0.9. So effectively, the frequency would increase just about by about 10%. Like I said, all this will be summarized in one equation to rule them all. did the opposite, if I were moving away from the source, effectively I would reduce the frequency I would observe by this expression here, actual frequency, velocity of sound, over the velocity plus the velocity of the source. I'm sorry, if the source were moving away from me. Then I would effectively reduce the frequency by that fraction. So putting all this together, come up with this. This is your one equation to rule them all. The observed frequency is equal to the actual frequency put out by the source times this fraction, which is the velocity of sound plus or minus the velocity of the observer over the velocity of sound minus or plus the velocity of the source. When using this equation, the top signs refer to motion that is toward the other object, and the bottom signs refer to motion that is backing away from the other object. Toward for top, backing away for bottom. A little bit of alliteration. In order to figure out what is toward and what is backing away for particular objects, this is what you should do. If you're thinking about the observer, the numerator of this equation, then you put yourself in the shoes of the observer. So I'm in the shoes of the observer, and I know that somewhere over there is the source. Right? If I am, as the observer, with my velocity, if I'm moving in that direction, whatever the source is doing, I don't know what the source is doing, but I know it's over there somewhere. If I'm moving in that direction, I'm moving toward the source. So I would use the top plus sign in the numerator, but that is what I was doing. Or if I'm the observer and the source is somewhere over there, and I'm moving this way, I'm backing away from the source. No matter what the source is doing. I just know it's over there somewhere, and I'm moving away from it. All right? That's how I would approach that in the numerator. It seems obvious, but I'm going to explain why this is not so obvious. But you've got to put yourself in the shoes of the respective item. The observer, if I want to look at the denominator, I put myself in the shoes of the source. All right? So here's the source, and let's say the observer is somewhere over there. And I don't know what exactly the observer is doing. The observer could be moving toward me. The observer could be backing away from me. I don't know. But I know the observer is somewhere over there. If as a source, I move in that direction, I'm moving toward the observer. So I would use the top minus sign for the source part of this equation in that denominator. Or as a source, I know the observer is somewhere over there. If I move in the opposite direction from the observer, then I'm backing away. And I use the bottom plus sign in the denominator for the source part of this equation. Got it? One Doppler equation to rule them all. You just have to put yourself in the observer's shoes first, in the source's shoes second. See what they're doing with respect to the other. Because the problem is they both could be moving, right? And possibly as the relative motion could be as a total toward each other, right? And so how do you deal with that? You'd say, well, they're both toward each other because the relative motion is getting toward. No. Just use that for your intuition. Just use that for your overall intuition to say that, yeah, the frequency should go up. But to use this formula, you got to put yourself in each shoes, the observer and the source. All right, what are they doing with respect to the other? Let's try an example. Here's a problem. An ambulance travels 75 miles per hour. The siren emitting sound at a frequency of 400 hertz. What frequency is heard by a passenger in the car traveling at 55 miles per hour in the opposite direction as the car approaches the ambulance? 1 mile per hour converts to 0.447 meters per second. That might be a nice little conversion that you might want to remember. I mean, it's easy enough to do. You could say that there are 1,609 meters in a mile and 3,600 seconds in an hour. And so if you have 1,609 divided by 3,600, you get 0.447. Nice to know. So, the car is moving toward the ambulance. We use the top plus sign in that formula. The ambulance is moving toward the car, because they're both moving toward each other. Top minus sign for the source. Here's the ambulance. Velocity of 75 miles per hour, or 33.5 meters per second. Here's the observer. Velocity of 55 miles per hour, or 24.6 meters per second. If I apply the Doppler formula, then the observed frequency will be equal to the actual frequency put out by the source, 400 hertz, times the velocity of sound, 343 meters per second. The observer is moving toward, so we'll use plus 24.6 meters per second for the observer, over the velocity of sound, 343. The source is moving toward, so we use the top minus sign, 33.5 meters per second for the source. Both of these are effectively helping to increase the frequency. And we get a frequency of 475 hertz. So that's what the observer would hear. I know this doesn't quite look like an ambulance, but when I first did the internet search for ambulance, this is what came up. So this was a few years ago. I'm sure there's better ambulance pictures now. Let's say they pass each other. So the car's on the other side of the ambulance is on the other side of the car. And as you put yourself in each other's shoes, put yourself in the car's shoes, ambulance is over there, the car is moving back and away. Put yourself in the ambulance shoes, car somewhere over there, and we're backing away. So they're both backing away. You're going to use the bottom signs for both of them in that equation. So we have 400 hertz, 343, bottom minus sign, 24.6 for the velocity of the observer, 343, bottom plus sign, 33.5 for the velocity of the source. Now you hear 339 hertz. It's not a perfect difference on either side of 400. You know, when the two are approaching, it's 475 hertz. When the two are backing away, it's 339 hertz. So it's not, you know, because of these mitigating things going on, you know, dividing and multiplying on top, it's not perfectly symmetric on either side. So you just have to put it in.
Is this at the moment that they pass each other? I mean, how does it happen?
This would be right after they pass each other. And for that time that they are continuing with those speeds away from each other. So when they actually pass each other, it's going to switch quickly from 475 hertz down to 339 hertz. That's where you hear that meow. That part. Right? That's when it's going to switch.
So even when they're like really, really far apart, you still.
It's still 339. If they continue with the same speeds, if they change their speeds, then that frequency could change. But if they continue with those same speeds, then it will continue at that same frequency. Let's try it. Actually, let's skip this one. That problem actually could tell you how, in a sense, a radar could determine your speed by using a Doppler shift. So you could actually find the speed of the observer or the sense. Since you're the source, and when you bounce it off the observer and it comes back to you, there's going to be a shift in that frequency, and by measuring the shift in that frequency, you can determine the speed of that object. That's how basically radar works. Take a look at this problem. A fire engine moving to the right at 40 meters per second sounds its horn at a frequency of 500 hertz at the two vehicles shown below. The blue car is moving to the right at 30 meters per second, while the red car is at rest. The international symbol for moving really fast is the wheels are off the ground. And at this moment, the blue car is just passing the red car. Question is, what frequency is heard by the passengers in the blue car? All right. So we got this fire engine moving at 40 meters per second, blue car at 30 meters per second. Before we even put anything in the formula, what is your intuition about whether that frequency goes up or down? Down?
It goes up
Why?
because blue car is moving slower than the fire truck.
Yeah, as an overview, you can just look at the whole situation. And the blue car is moving slower than the fire truck. So in relative motion, they're actually moving closer to each other. Right? So your intuition for that is that the frequency should go up. Even though there are mitigating things going on. The blue car is backing away, and the fire engine is moving toward. So those are mitigating, but the end result is, since they're moving closer to one another, the frequency is going up. But that's the only time you want to think that way, is just to get overall intuition for the problem. Because in order to use the formula, you want to put yourself in each of their shoes. So for the blue car, as we said, the observer in the blue car is backing away from the source. It is the intent of the blue car to get away. Somewhere over there is the fire engine, and I'm backing away, even though the fire engine is closing on me. All right? So even though essentially we're getting closer, but it's my intent to get away. So somewhere over there is the fire engine, and I'm trying to get away. I'm backing away. The source is moving toward the observer. So in our Doppler formula, the observed frequency will equal the actual frequency, 500 hertz, times the velocity of sound, 343, and we'll use the minus sign because the observer is backing away, so we'll use the bottom minus sign, 30 meters per second for the velocity of the observer, over the velocity of sound, 343, and we're going to use the top minus sign in the denominator because the source is moving toward the observer at a speed of 40 meters per second. When I figure all this out, my final frequency is 517 hertz. So it actually did go up a little bit. What about the red car? The red car was stationary. Fire engine's moving toward the red car. The observer is stationary, so the velocity of the observer is 0. Source is moving toward the observer. Apply the Doppler formula. We can just get rid of the velocity of the observer because that's 0. So it really doesn't matter plus or minus there. And we have the observed frequency is the actual frequency, 500. And in the numerator, we just have 343, the velocity of sound, plus or minus 0, over the velocity of sound, 343, minus the velocity of the source, because the source is moving toward the observer. So we use a top minus sign, and we get a frequency of 566 hertz. So, we have this situation. We've got a fire engine moving in. We've got two cars, a blue car and a red car. The blue car is moving past the red car at 30 meters per second, but at that moment, they're at the same place, basically, in the universe at the same time. Right? Because we're just looking at the moment where the blue car is passing the red car. So we have the car, the van, the red car and the blue car. I need to do a little updating there. Are at the same place in the universe at the same moment in time, yet they hear different frequencies. Wow. Really? So you have two observers who are at the same place in the universe at the same time, and they hear totally different things, and it's perfectly all right according to physics. Wow. That's interesting. How could you use this to your advantage? Let's say the defense calls you in as a star witness. They pay you a fee of $1 million. And they say, and basically you go up there and say, you know, we know you have 5 witnesses who saw my client steal the money. Right? However, in physics it says that you can have 2 observers at the same place at the same time, and they can observe totally different things, and it's all right. And so we got one observer over here that says my client definitely did not steal the money, the $2 million that he's been reported to have stolen. $1 million going to me for my fee. That he didn't steal, but and it's perfectly all right, right? Because physics says that observers can see things differently. It's perfectly all right. Wow. I'm going to do that, and then I'm going to retire. Because my reputation will be ruined. Okay, so I'm going to stop the Doppler talk right there, because we can look at more examples on the board. I want to get a start on chapter 18. I don't have to do as much on Monday. And then we can spend more time on Monday going over the sample test that you're to receive today. Suppose I had a string. I have a string that is tied to the wall. I initiate a pulse on this string, a wave pulse, and the wave moves down the string, and the string moves in a transverse direction as this energy of this wave travels along the string, and the string encounters the wall. As the string encounters the wall, we have forces going on between the string and the wall. There's tension in the string, and the tension is pulling on the wall. So as I look at this, tension is pulling on the support of the wall in the direction of the string. So as the pulse comes in, the tension is pulling along the direction of that pulse where it's connecting to the wall. Well, according to Physics 1, Newton's laws of physics, and in particular Newton's third law, for every action there's an equal and opposite reaction. So as the cord, the string, is pulling on the wall is pulling back with an equal and opposite force. So as the string is pulling with this tension in one direction, the support is pulling back with an equal and opposite force. Hence, the external force on the string is a force that is exactly opposite to what the string is doing at that moment. The string is a pulse that's going up like this, and the force on it is a force that is exactly opposite to what it is doing at that moment. The net result of that then is to actually invert what it is doing. If it was up like this and being pulled the other way, it's going to come out going down, or invert it in a reflected pulse. Let me do that. It's going to come out looking exactly inverted to what it came in looking like because of this reverse force of the rigid support. Net effect is, if I initiate this pulse against a rigid support, the pulse will come in, come out, inverted. If I did that with a bunch of pulses, I could have a pulse come in, and I could have inverted pulses coming out, and they might interfere with each other. Well, let's think about that. Consider two sinusoidal waves traveling in the same medium with the same amplitude, frequency, and wavelength, but they are traveling in opposite directions. So we have two waves traveling in opposite directions, basically the same type of wave. We're going to describe one wave, y1, as equal to some amplitude a naught sine kx minus omega t. The minus meaning it is traveling to the right. And the wave that is exactly equivalent would be y2 equals a naught sine kx plus omega t. Exactly equivalent wave, but it's traveling to the left because of the plus sign. Two equal waves moving in opposite directions. This could happen, as we just said, if I were to keep on initiating waves and have them bounce off the rigid support. So the waves are coming back in the opposite direction. So it might look like this. Initiate this wave, bounces off. Actually, when it inverts, this lower part inverts up, and the upper part inverts down. And so the wave coming back actually looks like the same wave, it's just in the opposite direction. Well, at different periods of time, with these two waves moving in opposite directions, we can have different kinds of interference. If the two waves, which actually have the same wavelength, but they actually were perfectly on top of each other, then we could have total constructive interference. And hence, if each wave has an amplitude A, when they totally constructively interfere, then the total result of that would be an amplitude of 2A. They'd go twice as large where they are totally in phase, constructively interfering. Whereas a moment later, you might have one wave going up and the other wave going down where they totally destructively interfere, and you've got nothing, as they totally cancel each other out. And then a little bit later, they go back into phase in the opposite direction, totally constructively interfere. The net result is an amplitude twice the individual amplitudes of the waves. Well, let's try to see what result we get mathematically for these waves. If I were to add these two waves together, y1 and y2, I would add a naught sine kx minus omega t plus a naught sine kx plus omega t. I'm going to expand the sine functions using the identity that the sine of a plus or minus b is equal to sine a cosine b plus or minus cosine a sine b. Just going to expand those trig functions. So I get this nice expression for the addition of the two waves. Bear with me, I'm headed somewhere with this. So we got a naught sine kx cosine omega t minus sine omega t cosine kx plus a naught sine kx cosine omega t plus sine omega t cosine kx. This term, which is minus here, and this term over here, which is plus, are the same terms, So they're going to cancel out. And so my net result is my two waves add together as one wave equal to 2a naught sine kx cosine omega t. If I think of this first part, 2a naught sine kx as an amplitude for this combined wave, and then the frequency part of it is how the wave is changing over time as it moves back and forth. So it actually has a frequency equal to, angular frequency equal to the angular frequency of the individual waves. So it's still oscillating like a wave, like the individual waves, but it possibly, depending on what the sine kx is, it possibly can have an amplitude of twice as much. So we have what was called a standing wave. The amplitude of the standing wave depends on its location x along the string. Everything's moving with some same frequency omega, but the amplitude equals 2a naught sine kx. The position x along the string determines what your amplitude is. For instance, whenever sine kx is equal to 0, we'll have a minimum. And that will occur whenever x is equal to an integral number of half wavelengths, because k by definition is 2 pi over the wavelength. So 2 pi over the wavelength times the wavelength over 2 would just equal pi. So whenever x is equal to an integral number of n pi, or whatever's in the sine is equal to an integral number of n pi, the sine function is 0. Sine at pi is 0, sine at 2 pi is 0, sine at 3 pi is 0, and so forth. So this would make that happen. So x equal to an integral number of lambda over 2, we got 0. That will occur at this endpoint here, and that will occur here, here, and here for this particular standing wave. So that's x equals 0, x equal half wavelength, x equal total wavelength, x equal 3 halves wavelength. What this means, in general, is that if we set up a standing wave, the distance between two successive nodes is a half wavelength. And we'll have a maximum whenever x is equal to an integral number of quarter wavelengths, where n is equal to 1, 3, 5, 7 odd integers. So we'll have a maximum at x equal lambda over 4, x equal 3 lambda over 4, x equal 5 lambda over 4. The distance between two successive maximum positions is actually a half wavelength as well. Two successive maximum positions. So here are some possible standing waves. Actually, we can have, well, we have the string itself, that's not a standing wave, but if we oscillated into one lobe, that would be what we call the fundamental frequency, and hence the whole string will represent half a wavelength. And so the length of the string itself would be 1/2 wavelength, wavelength would be twice the length of the string. We call these positions where there's no movement, either on any of these representations, we call those nodes. Now all nodes, all successive nodes, are half a wavelength apart. Hence we call the maximum positions on all these representations the antinodes. So maximums are antinodes, and they are spaced in successive order, half a wavelength apart. So you can measure the wavelength by measuring the distance between either two nodes or two antinodes, and then multiply that distance by 2 for any standing wave. A node and an adjacent antinode are spaced by a quarter wavelength. Remembering that all points vibrate at the same frequency omega, so the whole string is still vibrating. It's just vibrating more extensively at the antinodes than it is at the nodes. And the nodes basically are no amplitude, but they are still kind of shaky. They're basically stationary, but everything still has the same frequency omega, angular frequency omega. So it might look something like this. Alright, what we have here is an oscillator here that's producing waves on the string. They're moving down and bouncing off the fixed support and interfering, hence setting up the standing wave. The standing wave has two lobes. The distance between a node and another node is half a wavelength. So actually the wavelength of this standing wave is actually the length of the string. So we got half a wavelength plus half a wavelength. So for this particular standing wave, the wavelength of the wave is the length of this string between here and the support. In fact, if I want to look at that wave, well, let's wait for a second, because I need to turn the screen off. Let's try this problem. Two harmonic waves traveling in opposite directions interfere to produce a standing wave described by y equal 1.5 meters sine 0.4x cosine 200t. We can still extract information from this combined standing wave. There's k, there's omega, and there's our total amplitude, or twice our amplitude of the interfering wave. Determine the wavelength, frequency, and speed of the interfering wave. So there's 2a dot there, there's k, there's omega. And since we can still find k and omega, we can find the wavelength, the frequency, and the speed. Wavelength is 2 pi over k, 2 pi over 0.4, 15.7 meters. The frequency is omega, angular frequency divided by 2 pi. 200 divided by 2 pi is 31.8 hertz. There's our wavelength and frequency. So the speed of propagation is a wavelength times the frequency. 15.7 times 31.8 gives us 500 meters per second. So that's the speed of the interfering wave. Or equivalently, I could take in omega divided by k, which would have been 200 divided by 0.4, and that would give me 500 meters per second as well. So here's our standing wave, and in fact, for a wave with two lobes like this, it really is one wavelength that's moving really fast up and down like this. So to your eye, it looks like just two lobes of string. Right? In reality, when one string is up, the other part of the string is down, and they're just kind of moving back and forth like this. Like I said, I'll show you that in a moment. Here's the length of the string. Every distance between any two successive nodes is half a wavelength. So in this case, I would say the string is equal to total wavelength. The length of the string in general would be equal to an integral number of half wavelengths, no matter what kind of pattern we set up. So possible standing wavelengths correspond to twice the length of the string divided by n, where n is an integer of 1, 2, 3, 4, and so forth. since we know that the frequency equals the velocity divided by the wavelength, the possible frequencies that would cause standing waves would be equal to the velocity on this string divided by the wavelength that we just introduced. So that would be n over 2L times the velocity on this string. But we know that the speed of a wave on a string is equal to the square root of the tension divided by the mass per length from the previous class. So the frequencies that will cause standing waves are equal to n, where n is an integer, over 2 times the length of the string times the square root of the tension in the string divided by the mass per length of the string. So there are specific frequencies that will cause this to happen. We call those frequencies harmonics. So you have the first harmonic, the second harmonic, the third harmonic. All are frequencies corresponding to n in this formula. It all depends on what tension and what kind of string we use. If we say that the first frequency, n, equal to 1, is the first harmonic, it's also called the fundamental. That's the lowest frequency that would cause a standing wave. That would be the one where we have just one lobe over the whole length of the string. All other frequencies are integral multiples of the first frequency. So all other harmonics will be n times the fundamental frequency. And that will cause successive standing waves. Actually, before I do that then, here we have a standing wave with 2 lobes. I'm trying to set the strobe as best I can. It's hard to do. The same frequency. When you get close, you can kind of see what the string is doing. When this part of the string goes up, that part of it goes down in reverse direction. Right hand there. So you can clearly see that actually one way, which is up and down, is the length of this string. In other words, each lobe is half a wavelength, one full wavelength for the length of this string. That is n equal 2 harmonic that is n equal 1 harmonic. So that's the fundamental right there. So in this case, the total length of the string is 1/2 wavelength. And if I multiply that, if I figured out that wavelength, which would be twice the length of the string, multiplied by this frequency, I would get the speed of waves on the string. go the other direction. N equal 3. N equal 4. N equal 5. Let me go up a couple here. See if you can figure out what N it is. Let's see. Eight. N equal 8. Nine. How many is that? 11. The theory is if you go too high, you might create this continuity in the continuum, creating a black hole, which might. So we got to worry about that. Kind of get the idea. Well, if I want to measure the wavelength of this, I can measure just that distance. That'd be half the wavelength. Okay. So actually, two of those would be, there's a wavelength right there for these waves. At n equal 12. If I took that wavelength, right now the frequency is at 156 hertz. Okay. So I multiply that distance by 156, I get the velocity of wave on the string, which is not changing. The velocity is constant, right? Because the velocity is equal to the square root of the tension divided by the mass per length. The tension is constant the whole time, and the mass per length is constant. So the velocity is not changing. So in other words, as I change the frequency goes up, the wavelength is inversely shorter, so that the product of the two is constant. Just want to see if I can play a song. I was trying to play Yankee Doodle. It's not gonna work. Don't quit my day job. We do have Wes as a musician. So you should come up here and play something.
I'm a drummer.
We've got a few minutes. Let's at least do one example of a Doppler problem on the board. Take a look at number 18. No, number 17. I'll let you look at 18. We'll maybe look at that on Monday. 17. A truck moving at 36 meters per second passes a police car moving at 45 meters per second in the opposite direction. If the frequency of the siren is 500 hertz relative to the police car, what is the frequency heard by an observer in the truck after the police car passes the truck? Speed of sound in air is 343 meters per second. On 1717, truck moving at 36 meters per second passes the police car moving at 45 meters per second in the opposite direction. So velocity of the truck, which will be the observer, and it's 36 meters per second. And we have police car. Moving in the opposite direction, which would be the velocity of the source at 45 meters per second.
He's sitting on top of the engine.
Yeah. So don't quit my day job either. Become an artist. Frequency of the siren is 500 hertz. It says as observed by the police car. Let's see, how do they say it? Frequency of the siren is 500 hertz relative to the police car. So what that means is if you're right there, you know, you're right there with the siren, so that is the actual frequency of the siren. Okay. 500 hertz. So they're approaching each other like this, and so the observed frequency should equal the actual frequency, velocity of sound, plus or minus velocity of the observer, velocity of sound, minus or plus velocity of the source. Let's go ahead and write down the full Doppler equation. I just noticed that 18 is kind of related to this. What's the frequency heard by an observer in the truck after the police car trapped? So 16 is as they approach, 17 is after they pass each other, and 18 is the difference in frequencies between the two. So let's treat this as 16 first, 17, and then 18. Let's do all three. So as they approach, we would have the observed frequency equals the actual frequency, 500, times velocity of sound, 343, plus or minus the velocity of the observer, which is 36, over the velocity of sound, minus or plus the velocity of the source, which is 45. So, as the two are approaching, what should I use in the numerator? Plus sign. Because the observer is moving toward the source. And in the denominator, minus sign. Because the source is moving toward the observer. I use the top signs in both cases. What does that give me? At 635.9. Two things going on, increasing the frequency. We're both moving towards each other, so that's going to increase the frequency a lot. They pass each other, so they're both receding. Now the truck is over here. The police car is over here. observed frequency would equal the actual frequency, velocity of sound, plus or minus the velocity of the observer, or the velocity of sound, minus or plus velocity of the source, which would be 500 times 343. Plus or minus 36, 343 minus or plus 45. Numerator, I should put
Once.
minus, because it's the intent of the observer to back away from the source. Yeah, so the observer, somewhere here is the source, the observer is here, the observer is trying to get away from the source. And in the denominator, plus. Same thing. So the intent of the source to back away from the observer. I put that data in there. Oh, again. $395.6. So as they're approaching, the observer heard 635.9 hertz. As they passed and are going the opposite way, 395.6 hertz. It switched real quickly as they actually passed each other. And so, this is the answer to column number 16. This would be the answer to column number 17. And number 18 is what is the change in frequency as the two pass each other. So the change in frequency would be F1 minus F2, at least in magnitude. So that would be 635.9 minus 395.6. So there's 241.3, right?
It's 40.
240.3. Perfect. I got 240. So if I put one of these on the next test, okay, that's what I want to hear. These are suggested types of problems that might be similar to the kinds of problems you should expect on the first exam. Right now, theoretically, you should be able to do problem number 1, problem number 2, problem number 3, 4, 5, 7, and 8. You probably can do pretty well with number 6. Can't do 5. Okay, we haven't done 5 yet. That's the only one which is totally out of the question. Not totally out of the question. We'll talk about that Monday. But the rest are fair game. So take a look at this.